In this video, we're going to look at the Lagrange error bound, and this is a way to know how far off a Taylor or a Maclaurin polynomial will be from the exact value of the function that we are approximating. So first off, Lagrange error bound. So this is some way to sort of calculate the maximum possible error for a Maclaurin or Taylor polynomial, so long as the series converges where we're looking. So in here, very similar. It's a lot like the remainder theorem, which I put up in the last video, but here is the Lagrange error bound for the Maclaurin polynomial. So the error must be bounded less than or equal to the maximum for all t in the interval from 0 to x of the derivative, the magnitude of the derivative, or the n plus first, the next derivative of t, divided by n plus 1 factorial multiplied by x to the n plus 1. Now, little explanation, some ideas here, and then I'll put the Taylor beneath. So there are three parts to this. We have this right here, which is by far the trickiest part of this. I need to find the maximum amount that the next derivative takes, the maximum value, the maximum magnitude the next derivative takes. The other two parts are going to sort of plug in, but this takes some doing. When we see some examples, you'll see how we figure that out. But it should make sense in that the nth degree Maclaurin or Taylor polynomial deals with the first n derivatives. The next thing that makes the biggest difference in that function is the n plus first derivative. And the biggest difference it can make is the maximum magnitude it has. If it has a very large positive number, it's going to drag my my actual value above the approximated value. If it has a very large magnitude negative number, it's going to drag the actual value below what the estimate has. And this will tell me how far it can pull it. It'll bound it. Okay? For a Taylor polynomial, the error has to be less than or equal to the magnitude. I still have this max. Now we're looking at t values in the interval from a to x. We have some center here of the next derivative, all divided by n plus 1 factorial, because we've sort of gotten to the n plus first derivative. If we take n plus 1 derivatives of x to the n plus 1, we get an n plus 1 factorial. And I have x minus my center to the n plus 1. And I guess, so we talked about this. Now, it should also make sense. As I add more terms to my Maclaurin or Taylor series, they generally get to be better estimates. So this n plus 1 factorial will drag it back down. The bigger n is, the bigger this denominator will be. Hopefully the smaller the error becomes. Also, the closer I am to my center, the center for this being 0, the smaller it should be. So this right here, when I'm close to 0, this will be a small value. When I'm far from 0, this will be a large value. Or in this case, I'm centered at a. When I'm close to a, this will be a small value. As I get further from a, this will be larger and larger. So all three of these parts should make sense to us in both of these. The question is, okay, how do I remember them, or why is this the case? Now, I'm going to outline a derivation for it. As with the remainder theorem, I'm not going to be completely rigorous. It would take a long time. It would probably be a very poor explanation. There are some completely rigorous derivations shown online or in many textbooks. But here's the idea, and I'll show it just for Taylor. So recall that the remainder theorem shows that the remainder of the nth degree Taylor polynomial will be the n plus first derivative of some c in that interval divided by n plus 1 factorial multiplied by x minus a to the n plus 1. And sort of the biggest magnitude possible comes from the maximum for, let's say, c in the interval from a to x. Again, I'm being a little bit loose. If x is smaller than a, it should be flipped order of this derivative. Because everything else is sort of set. We have an x, we have a center, we have an n, but this up here, we don't know where this c is, from where the c is coming. It can come from anywhere in that interval depending on how it works out. So the maximum error, so let me change colors. This implies the maximum possible error comes when I toss this into that remainder theorem. So this is the actual amount we are off, either positive or negative, but I don't necessarily know what this c is. However, I know that the maximum possible it can be above or below comes from the max for c in this interval, 9k, of the next derivative over n plus 1 factorial multiplied by how far I am away from the center to the n plus 1. And since it's an error, all errors are positive. We put in those absolute values. So that's the Lagrange error bound. Now let's see how it works. And actually not too bad. I just need the three pieces. I need to find this, the maximum of the derivative. I need to do this factorial. I need to figure out how far I am from the center. If I can do that, I can get this error. So here's an example. Use the Lagrange error bound to calculate the error in using the Maclaurin polynomial degree 4 for f of x equals cosine x to approximate cosine of 2. So I have the three pieces. I need to find the max for my values in the interval from, it's a Maclaurin polynomial, so 0 up to 2 of the n plus first, sorry, not n plus 1, because I have n here. If this is degree 4, then I have the fifth derivative of x, but evaluate at c. I need to have n plus 1 factorial, which is going to be 5 factorial, and I need to have x to the fifth. That's going to be 2 to the fifth. Those are the three things I need. All right, well, the fifth derivative of cosine is negative sine. I'll write that down. So this will be the maximum for possible t values. Oh, this should be a t, sorry. In 0 to 2 of negative sine of t. Well, the biggest or smallest t can be our positive or negative 1 respectively, so the biggest this magnitude can be is 1. 5 factorial is 120, 2 to the fifth is 32, and that means that my error is less than or equal to, I have my maximum, which is going to be 1, divided by n plus 1 factorial, which is going to be 120, multiplied by x to the n plus 1, which is going to be 32. You can see just 1, 2, 3 parts you put in there. We get that the error is less than or equal to 32 over 120. And let's reduce that down. So let's see. 120 has 16 in it. Is that correct? So I can divide both by 16. When I divide the numerator by 16, I get 2. When I divide the denominator by 16, let's see. Ooh, did I just lie? I did just lie. It doesn't have 16. It only has 8 in it. So divide the numerator by 8, I get 4. Divide the denominator by 8, and I get 15. So this fourth degree approximation cannot be off by more than 4/15. Now that's the answer. You might be wondering, how can I use that? Well, let me show you another example, and I'll show how this plays in to being useful. So we're given some information about a function g, and we're told something about its fourth derivative. I want to estimate g of -4 and find an interval. And this interval is the useful part. So, first thing, I want to find I can find a third degree Taylor polynomial. So let me put this down. The third degree Taylor polynomial evaluated at x is going to be 2 over 0 factorial. Then the first derivative is 4, so plus 4 over 1 factorial times x plus 3 to the first. The second derivative is 6, so I have 6 over 2 factorial, which is just 3, x plus 3 to the second. And the third, I have 24, that's 24 over 3 factorial, that's 24 over 6. So that's going to be 4 times x plus 3 to the third. So that is my third degree Taylor polynomial, which I can then use to estimate g of -4, which is going to be approximately that third degree polynomial evaluated at -4, which is equal to 2 plus 4 times -4 plus 3 is -1, plus 3 times -4 plus 3 is still -1 squared, plus 4 times -4 plus 3 is -1 cubed, which is equal to, let's see, so that's going to be 2 minus 4 plus 3 minus 4, -3. So that is my approximate value of g of -4. But the obvious question that you should be wondering is, how close is that? Because it's an approximation, I want to get close enough. And how do I know if I get close enough? And that's where we use the Lagrange error bound. So my error, I know has to be less than or equal to, I have the max. I'm just gonna write maximum here divided by n plus 1 factorial times the distance, which is going to be sort of x minus a, which is going to be x plus 3 to the n plus 1. Okay, so this error, the maximum this derivative can be is 4. So they just give it to us. We have the third degree polynomial, so I will have 3 plus 1, which is 4 factorial. And then I need to see how far I am from my center. -4 is -1 from my center. It would be this -4 plus 3 to the fourth. So I have 4 divided by 24 times -1 to the fourth is 1, which means that my error has to be less than or equal to 1/6. And this is where it gets really useful. So the error is less than or equal to 1/6, which means that g of -4, let's write it this way, g of -4 must be greater than or equal to this minus 1/6 and less than or equal to this plus 1/6. If my error is 1/6, then I'm between these. And when I just do the work, so -3 is the same thing as -18/6, so I get -19/6 is less than or equal to g of -4 is less than or equal to -17/6. And this is where it gets really useful. So I can clearly see exactly where this has to be. I think it's -3, but I also am pretty sure it's going to be a little bit off because this only took into account the first 3 derivatives. There are more. But this I know with certainty because what makes the biggest difference or the biggest leftover is the fourth derivative, and the fourth derivative gets no bigger than 4 or no less than -4. If it were -4 everywhere from -4 to -3, then we would actually get to this point. If it were +4 from everywhere between -4 and -3, then I would get to this value. And if it's somewhere between those, then I'll be somewhere between these values. But that's the idea. I hope this helped out. Feel free to comment below with any questions, and I'll get on to some more stuff later.